Hello and welcome to another segment of Geology 1 Processes and Products Lab DVD. My name is Renee Clary and today we will talk about rivers and streams and running water. Running water is the most important geologic agent. It's the most important agent of erosion. It's not the most powerful because that honor goes to a glacier. A glacier can move much bigger rocks and boulders than a river can. However, rivers and streams are the most active and the most important agent of erosion that we currently have on our Earth. All geologic agents erode, transport, and deposit. With rivers and streams, we see erosion in many different forms, but especially along cut banks. We'll identify cut banks in a slide in just a minute. Rivers can transport in solution minerals, ions. We can also transport in suspension fine-grained silt and some sands. And finally as bedload, where bigger particles are rolled or saltated along the bottom. Now we're not going to discuss transportation in this lecture, but your book and your lab manual may have more on transportation by running water. We will look at the deposition by rivers, including deltas, natural levees, and point bars. There are different types of streams. We can have straight streams, braided streams, and meandering streams. And as you might imagine, a straight stream simply means that the water's moving in essentially a straight line. And these form in areas of high elevation. The second diagram shows us a meandering stream. In this one we have one main channel and it tends to travel in broad looping curves. And finally the bottom diagram shows us a braided stream system, and in this system we have a lot of different channels that will break apart and merge back together and break apart again. One characteristic of this stream system is that it carries a huge sediment load, and as the sediments are deposited the water will move around the sediments, splitting the channel and then reforming again. Okay, so braided streams, we have a large sediment supply. This happens in deserts and in glacial areas. The channel is very broad and very shallow. We don't have carved out channels like we do in a fluvial system. And because the water is transporting so much sediment, the channels keep getting clogged with sediment and they split and they rejoin. Let's look at a photograph of that. Here we go. We have water moving and it's carrying a lot of sediment. You can see all of the sediment within the channels. Here the sediment is deposited so the channel simply splits around it and reforms later. This is a braided stream, again fairly common in arid regions and also in areas where there is a lot of glacial outwash because there's a huge sediment load. What about meandering streams? Well, chances are this is the type of stream you think about when you hear the word river or stream. These are the most common. They have one channel, a single channel, and the river travels in very, very broad looping curves. The river is not static. It will erode on the outside of its channel and it will deposit on the inside of its channel, and therefore the river will migrate across its floodplain and oxbow lakes typically form. Well, what are those? Let's take a look. Here we have an overhead aerial view of a meandering channel. See how the river travels in very broad looping curves. And occasionally we see these little crescent shape lakes. These are oxbow lakes. Once these were part of the original channel of the river, but because the river's dynamic, it does change its path. With meandering streams, we tend to erode on the outside of each curve and deposit on the inside of each curve. The erosion takes place on the outside of the curve, or the cut bank, and the deposition takes place on the inside of the curve, or the point bar. Now those oxbow lakes that we just saw, let's go back there, these oxbow lakes are cut off meanders of the river. Here we see a nice diagram. This dashed line shows us the area where we have the highest velocity of water in the channel. That's referred to as a thalweg, T-H-A-L-W-E-G, thalweg. Now, where the water travels the fastest is where it can do the most erosion. And here, as you see on the outside of that curve, we have a cut bank. Notice the thalweg moves to the outside of this curve. Water travels faster here, so we have another cut bank. Water travels slower on the inside part of the curve, and therefore we get deposition or a point bar. Here is a point bar, and here is another point bar on the inside of that curve. This is a great photograph because it actually shows us the deposition of the point bar. You can see that the river travels fastest along the outside part of the curve, and this is where our erosion is taking place. Our deposition is on the inside of the curve, or the point bar. So, how do we get those oxbow lakes? Well, let's look at the formation of an oxbow. Here's our river channel. Now remember, we are going to erode on the outside of a curve, so we're going to erode here, and here, and here, and we're going to erode here. So over time, our stream channel's actually migrating, and in this case, we have two parts of the channel getting very, very close to each other. During a flooding event, and flooding events are natural, during a flooding event, the water will jump this narrow little neck, and the river will assume the new straighter path downstream. This former meander gets silted off with deposition, and over time becomes the remnant of the meander, or an oxbow lake. Okay, let's talk now about stream terraces. Sea level has not always been at its current level, so we know that sea level has risen and fallen many, many times over our geologic history. A stream terrace is the erosional remnant of a former higher floodplain. So, what this means, as sea level drops, the river carves deeper and deeper into its channel. Now, we've already shown how rivers do not stay in one nice little channel. Instead, what's going on is that a river will migrate across its floodplain. We'll have cut off oxbows as a result. So, as we develop one floodplain, and then the sea level drops and the river cuts deeper, or in many instances the land level is rising with respect to sea, but the river again cuts deeper, it will develop a new floodplain. This is what it looks like in a diagram. Here we have a meandering stream, and it's going to develop its floodplain, but if we have uplift of the land or a drop in sea level, the stream will erode down to the base level, which in most cases is probably the ocean level, which is the ultimate base level. So this former floodplain is now going to be a terrace elevated above the stream. Well, again, the stream does its job and it continues to meander and develop its floodplain, and now we see the current floodplain, but this former floodplain is preserved as a stream terrace. Here is our terrace, and here is our floodplain, and here is our meandering channel. I have a photograph of one as well. Note that the river is very, very tiny down here to give you some idea of scale. And here we see, this looks like it is a slight stream terrace. This looks like the current floodplain down here, but we definitely have a terrace here. This was the former level of the floodplain. We have a terrace here as well, and there may be further terraces outside the photograph. Okay. Rivers drain land, and a drainage basin is that area that is drained by an individual stream system. Now, a drainage basin can be separated from another drainage basin by a divide. We can have large drainage basins, and then we can have minor drainage basins within a larger one. Here we have a divide, which is a high area of elevation. So this would be a drainage basin. All water falling on this side of the mountain would drain to this system, and all water falling on this side of the mountain would drain to this system. This is our divide. We have two drainage basins. Now within a drainage basin, here we have a drainage basin for a larger drainage basin. Here's our divide here in the dashed line, but within we can also have minor drainage basins. Okay, note that here's an area, a topographic high, so water that falls on this side will flow in this direction off to the right, and water that falls on this side will flow off in this direction to the left. But we can have smaller drainage basins within the larger one as well. Drainage patterns develop dependent on the topography and the underlying rocks. We can have dendritic or root-like, rectangular, a trellis system, a radial system, that does sound just like what it is a circle, centripetal, annular, and if it doesn't fit into much, it's deranged. Dendritic is tree or root-like. This is what we typically think of in a drainage pattern. A radial system will develop like the spokes of a wheel from a topographic high radiating down. Rectangular systems typically develop along fault lines or joints in the bedrock. And with a trellis system, we have alternating areas of less resistant rock and more resistant rock. These yellowish areas are more resistant rock, and the greener valleys are the less resistant rock. So we tend to have little stream systems develop within the valley of the less resistant rock. So we have more eroded, it's at a lower level, and our main stream will cut through. This is a trellis pattern. We have a centripetal pattern where we are draining down into a basin, and of course there's no outlet here. This is a lake. We have an annular pattern, and this also arises very similar to this trellis pattern because of more resistant rocks to erosion and less resistant rocks. And finally, we have drainage systems that we really don't know what they fit into, deranged. This would be a pretty good example of something, let's say, in a karst topography where streams may start and stop and they have no real pattern, deranged. Okay, we're going to look at the gradient or the slope of a river, and we're going to do a little bit of a calculation. The gradient is simply the distance, the change in vertical elevation over the change in the distance it travels, the rise over the run. We're calculating the slope of the river more or less. It's usually steeper in these upslope sections, and it tends to flatten out toward the end or the delta of the river. Okay, let's go ahead and calculate the gradient for this particular topographic map. What I've done is to show you a couple of spots where the contour lines are actually crossing the river. So I've put an X where one contour line crosses, and I've put an X where another contour line crosses. And let's go ahead and take a look at that map. Okay, let's bring it down a little bit. Here we are. We have our two X's right here. There's a contour line. I don't know if you can pick it out with this resolution, but there's a contour line that passes right here. And it is at the elevation. It's in feet. It says our contour interval is 40 feet. So this one is 4,840 feet, where my first X is. And I've located another contour line down here. This is at 4,920 feet. So let's go ahead and figure out what the gradient is. I'm going to turn this sideways and use a straight edge and go from one X at the edge to my second X here. In order to find the distance traveled, what I need to do is to come back to my scale, and since we are looking at feet for our contour interval, we'll stick with miles. Use the bottom scale because it is in miles, and we have 1 mile, 2 miles. Basically right here we have 3 miles. Now remember, the contour interval the contour interval is 40 feet, but our contour lines are at 4,840 feet for this X, and for this X down here we are at 4,920 feet. Okay, let's calculate. The distance traveled is 3 miles. We just did that by looking at the distance between the 2 points, the 2 x's, and figuring that out with the bar scale. Now, the vertical drop will be the difference in our contour lines, 4,920 feet and 4,840 feet, and that comes to 80 feet, excuse me. So our gradient is going to be our rise over our run, our vertical over our horizontal, or 80 feet over 3 miles. So if we divide by 3, we end up getting 26.7 feet per mile. That is a gradient of our river. Before we end, we need to talk just a little bit about floodplains. Floodplains are those low-lying areas near streams that flood periodically with large volumes of water. Now, floodplains are natural, and flooding is natural. There are some less severe floods that occur more often, and then there are the 100-year floods that occur usually less than every 100 years. Floodplains develop with a mature stream. Now, the river has a natural way of building up its channel and its banks, and these are the natural levees. As the river floods and overflows, it deposits right along its channel, and we do get those natural levees. Of course, we're not content with natural levees, and we often engineer other man-made levees to keep that river in its channel. The land further away from the channel is referred to as a back swamp. Here we go. Here we have a meandering stream. Occasionally the stream will flood, and we will see some buildup along the channel. This is its floodplain, and it's quite a natural place for the river. And note what happens when it does flood. It will deposit sediments right alongside its channel. These are natural levees. Now, do natural levees, or even man-made levees, always keep the water in place? No. One problem with levee systems is that by channeling the water, we don't allow the periodic floods to replenish the floodplain and also to build up the river naturally. So this means that the water, first of all, we're straightening channels sometimes. We're moving the water through pretty rapidly. If the water is going to deposit sediments, it can't do so on the sides because we have that levied too high. So the river may deposit sediments even along the bottom. Well, what happens to the level of the river? Well, it rises, so we either dredge or we build our levees higher. And even then, we never know when we're going to have a flood, a 100-year flood, 50-year flood. Of course, smaller scale floods are fairly common. Well, that concludes the lecture today on streams, rivers, and stream processes. If you have any questions about calculation of gradient or any questions about any material that was presented, please feel free to email your instructor. He or she will be happy to answer your questions. Thank you very much for joining me, and have a great day.